Okay, we're in this lesson 7.4, graphing rational functions, and just to help some of you, I know sometimes these graphs of rational functions can be a little challenging for some people. So I've selected 3 of your 10 homework graphs to work out with you on this video, and then there's a separate video already on Moodle that has the workout of, I think it's number 28, but you can go on Moodle and check that out. But I'm going to work out numbers 1, 6, and 16 on this. Now, again, I say this a lot, but don't let the watching of this video and don't let it just stop there. You need to, if you need to watch this whole problem being worked out, or all 3 of these problems being worked out, then you need to go back and do them yourself with no help and make sure that you are able to go through this whole process, because that's what you're going to be expected to do on the test. So just watching me do it, if that's where it ends, is really not going to be very helpful or as helpful. Okay, so let's get started. The graph of this rational function, first of all, I'm going to factor everything I can factor. The numerator is not factorable, it's prime, but I can factor the denominator. And there's a couple of really good reasons for factoring. Number one, I might be able to reduce the fraction, which makes it a little bit easier to graph, to do inputs and outputs. And also it makes it easy to identify those vertical asymptotes. If nothing does cancel these denominator factors out, then I know right off the bat, and I can't cancel, I know right off the bat that I am going to have 2 different vertical asymptotes, and we'll talk about that when we get down to our next step. But factoring everything out makes those numbers easier to see. So what I'm going to do in this first step, I'm just going to call it letter A, is I'm going to focus on the numerator, and I'm going to see if I have any x-intercepts. We also call these zeros of the function. Are there numbers that would make this numerator equal 0? Well, if I'm not sure, if it's not obvious to me, I can find out by doing this. I'll just take the numerator, make it equal to 0. And so far I've got x to the 4th equals 2. So I'm going to have to do the 4th root. I'm going to raise both sides to the 1/4 power. And that's just another way of saying the 4th root of both sides. So in my calculator, I'm going to see what the 4th root of 2 is. So if you're going to use your calculator for this, and you can do it by doing 2, and then that's upside down v to raise something to a power. You just need to make sure that you put 1/4 in parentheses. So you'll do left parentheses 1 divided by 4, close your parentheses, and you should see the number 1.1892 and so forth. But I'm just going to round that off, and I'm going to say that it's going to be plus and minus, because there's an even root. So you treat it just like you did with square roots. We're going to have 2 possibilities, plus and minus. We'll just call it 1.2. All right, so the first thing I'm going to do is I'm going to make these 2 dots on the x-axis to represent where I'm going to cross. I got 2 x-intercepts, just barely to the right of 1. I'm going to call that positive 1.2, and just barely to the left of negative 1. I'll call that negative 1.2. All right, and so we know that we're going to be crossing the x-axis through those 2 dots, or we're going to be touching the x-axis. Okay, so let's move on to step B. Do we have any vertical asymptotes? Well, we talked about that earlier. Vertical asymptotes are numbers that we plug in for x to cause the denominator to equal 0. And since I could not cancel either of these factors in the denominator, I'm going to have 2 vertical asymptotes. I'm going to have one x equals negative 1, because that causes this first binomial to be 0. And if that is 0 and I'm multiplying, then this whole denominator is going to be 0. 0 times anything is 0. And not only that, I'm going to have another vertical asymptote at x equals +1, because +1 plugged in for x causes this binomial to be 0, and 0 multiplied by anything is equal to 0. So I'm going to draw two vertical lines. Here is the line for the equation x equals +1. All right, so I will not have any ordered pairs for this particular graph. There will not be any ordered pairs, any points represented on this graph on this line. This is kind of an off limits, no ordered pairs. And then I'm also going to have a vertical line x equals -1. Real close to my x-intercepts. All right. Now, let's see if we have a horizontal asymptote. Well, let's compare the degrees of the numerator versus the denominator. The numerator degree is 4. The denominator degree is 2. And I told you in our class discussion that if the numerator degree is bigger than the denominator degree, then you will not have to worry about drawing a horizontal asymptote. Okay, so we found our x-intercepts, we found two different vertical asymptotes, we've sketched those, and now we're ready to see exactly where this graph is. It's really going to be one graph, but it's going to be broken up into three different parts. These two lines essentially break my graph up into three sections. So now we're going to find out where this graph actually is, and we'll do that by doing a table. Okay. So I'm going to work, first of all, just think of it this way. Find numbers that fall in this area to the left of this vertical line. Then we're going to pick some numbers that fall in between, or maybe we can just get by with one number. And then we'll pick some numbers on the right. So you're picking around, you're doing inputs around those two vertical lines. Okay. So let's see, a good choice for an input, for example, would be -2. All right, so let's see if I put -2 in for x, and it really doesn't matter which of these you use. If you want to use the original, or if you're confident that your factoring is correct, you can use the factored form. I think I'm just going to go ahead, since I'm only going to input twice instead of 3 times, I'm just going to use the original. Okay, so let's make sure we get our calculator set up correctly. The entire numerator, if you're going to use your calculator to do all of this work, the entire numerator needs to be in parentheses. All right, so let me see if I can talk you through it. I got left parentheses, then I'm going to do another left parentheses. So right now I'm looking at 2 left parentheses. And then I'm going to do -2. I'm going to close -2 inside its own parentheses. So I've got -2 in a pair. It's enclosed. All right, now I'm going to hit my raised to 4th power. Okay, and then I'm going to do minus. I noticed in class that some of you are treating minus as negative. So you need to be careful. If you're using the scientific calculator, to make a number negative, you use the very bottom key. And if you're going to do subtraction, you go up about 3 rows, and that's your subtraction key. Okay, and then we're going to put in 2, and now we're going to close parentheses. So right now, you're looking at 2 pairs of parentheses, a pair that encloses the entire numerator, and then another pair that just encloses -2. Okay, now we'll hit division. Okay, and now we're going to do the same type of thing with the denominator. I'm going to do left parentheses twice. I'm going to put in -2, close parentheses. I'm going to square that. And now I'm going to subtract 1, and then another right parenthesis. Okay, so let me read that off just to make sure, because once we get this put in, then it's easy just to go up and replace -2, and we'll leave everything else. So reading it off just like it's on my display, left parentheses, -2, right parentheses, raised to the 4th power, -2, right parentheses, divided by left, -2, right, raised to the second power minus 1 right, parentheses. Okay, let's hit equals and see what that gives us. And it looks like it's 4.6666. We're just going to say rounded 4.7. So for input -2, I'm going to go up almost 5. 1, 2, 3, 4. Here's 5, just below 5. We'll call that 4.7. Looks like I got a stray mark here. And my eraser is too big, so let's tone that down just a little bit. Okay, so that's pretty good information. I know that looks like I'm coming from positive infinity. If you're thinking positive infinity up here, I'm coming from there. I've got to go through this point. I know I've got to go through this point. I also know that I will never come back down on this side of this output and cross the x-axis again. I'm only going to cross x 2 times. Okay, so let's just for good measure, let's just go ahead and input -3 and get an even better picture of what this graph is going to do. So leave everything in your calculator and just change the 2 to a 3. All right, I'm doing that right now. I changed the 2 to a 3. I hit equals, and that's 9.875. I'm just going to say 9.9, just about 10. So for input -3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And now I'm feeling pretty good that that pattern is going to continue. As I input more negatives, I'm just going to get bigger values for y. So it looks like the left side of this is going to do this forever. It's going to come from negative infinity along the y, cross through, cross through, cross through, and then by definition, it's going to follow this vertical asymptote forever but never touch. But it'll increasingly get closer as y goes to negative infinity. All right, so that's one side, one piece of our graph. Now let's see what's going to happen in the middle. Okay, well, in the middle, a pretty easy input would just be 0. In other words, we're going to find the y-intercept. Anytime you replace x with 0, you're going to find out where or if it crosses the y-axis. Well, inputting 0 essentially just removes these two x terms, and you're left with -2 over -1, which is, of course, +2. Okay, so let's think about this for a second. There is no way that I could be coming this way and cross the x-axis. All right, so just for sake of confidence, let's do one more input in here and get a really good idea of where this graph is going. So let's input 1/2, 0.5. All right, so go back to your calculator and replace the -3 with 0.5. And that's what I'm doing. And I got 2.58333, so I'm just going to say 2.6. All right, so that's interesting. So for input 1/2, almost, we're going to say it's about 2.5. So 1, 2.5. All right, and I'm feeling pretty good. Normally, if you have vertical asymptotes like this that are evenly spread out from the y-axis, you're going to have symmetry around the y-axis. And so without even trying, without even plugging it in, you can be confident that if you do -1/2, you're going to get the same result. Okay, and so by virtue of the fact that these are vertical asymptotes, I'm going to be following them forever going up, never touching. So it's like we got a little parabola, skinny parabola in here in the middle. All right, and once again, you got a pretty safe bet that with vertical asymptotes that are surrounding the y-axis the same distance apart like this, you're going to have symmetry around this entire, well, for this entire graph. So I'm betting that when I put in positive 2, I'm going to get the negative, or the opposite. For positive 2, I'm going to get positive 4.7 to match up with this one. When I mean opposite, I meant corresponding, the corresponding point. So let's just see if that is true. Okay, so we'll just go up and we'll replace 0.5 with 2. And I'm doing that as well. And sure enough, I got 4.7. So you can kind of be on the lookout when your graph sets up like this, vertical asymptotes that are on either side, same distance away, they're symmetrical about the y-axis, then your entire graph is going to have symmetry. 2, 1, 2, 3, 4, and we'll say it's right there to match up with this one. And so it's going to do, really, it's a reflection of that other side. So we're just going to do this. And I didn't get close enough, but I think you get the idea. And that is my graph for this problem number 1. And that's pretty much the process. You're going to go through these steps every time, looking for vertical, horizontal asymptotes, looking for x-intercepts, and eventually even y-intercepts, like we did down here in the table. Okay, and now we'll jump over to problem number 6. Okay, so for number 6, I noticed that I do have a factoring opportunity in this numerator. It can be factored as x minus 5 times x plus 1. The denominator cannot be factored. It stays as x plus 1. Okay, so the great thing about recognizing factoring is that it enables us to cancel. So I notice that I've got these matching binomials, x plus 1. So I can cancel those. So what happens is I'm essentially going to be graphing the function f of x equals x minus 5, or you can think of it as y equals x minus 5. That's just going to be the graph of a line. Y equals mx plus b. The y-intercept is going to be negative 5. The slope's going to be positive 1. So it started off looking like a really complicated function that would be graphed, but as it turns out, it's just going to be a pretty simple line. However, there is a part that we need to make sure we understand, and it involves this canceling, and I'll talk about that in just a minute. So to begin with, we'll just follow our same pattern. Let's find out if we have any zeros or x-intercepts, and that means we will take this numerator the way it is now after canceling. Just take your numerator, let it equal 0, and solve. So we should be, with our graph, we should be crossing the x-axis at positive 5. All right, and so that should be an x-intercept for us. And so now let's look for vertical asymptotes. And this is kind of tricky for some people because you might right off the bat think, well, I have a vertical asymptote at x equals negative 1. But after canceling, we no longer have that vertical asymptote. This bottom part of the fraction, when canceling, essentially is gone. So there is no vertical asymptote in this case. Now in the previous problem, I wasn't able to cancel the denominator with a factor in the numerator. So I ended up having actually 2 vertical asymptotes. All right, so there's no vertical asymptote in this case because of the canceling. There's actually not going to be a horizontal asymptote either because of the same reason as before. The numerator degree is larger than the denominator degree. Numerator degree is 2. The denominator degree is 1. Whenever that happens, there's no horizontal asymptote. But there is a point of discontinuity. Discontinuity means it causes my graph to not be continuous. And whenever we have these matching factors, these matching binomials like this, where we canceled, the number that made these two, they're the same. The number that makes this binomial equal to 0 is the number -1. So at -1, where x is -1, I have what is known as a hole. And I'll show you what that looks like in just a second, but right now I want you to know when you have one. You'll always have a hole when you're able to cancel matching factors like we did here, and whatever made that binomial, or it could be a monomial, whatever it is that caused that expression that canceled to equal 0 will represent a hole in the graph. Okay, so letter C, in the past we've used letter C to make a table, but we don't really need a table to graph the line y equals x minus 5. That's just going to be a y-intercept of -5, and it's going to be a slope of +1, up 1, right 1, up 1, right 1. And you can kind of see how my x-intercept is going to come into play. I am going to cross the x-axis at 5. And this is just going to be a line that goes forever and ever, almost. Okay, remember the hole? I'm going to have a hole in this line where x equals -1 in the line. All right, so I'll go ahead and get my line draw tool. If you don't have a straight edge, just do the best you can. And I think I'm just going to arrow the ends, and I'll show you why. At this part where the hole is, my line actually, I think I'll make that a solid. The line actually doesn't go through that hole. The line actually jumps over where the hole is. So that's kind of a rough sketch. Probably should make that a little more accurate. It's a little bit better. So the whole idea of a hole is I've got a continuous line except for one little spot in this case. My line does not pass through where x would be -1 on this line. Okay, so if I just think of it this way, if you did input -1 in for x in this linear function, you would get -6. So at the point -1 input, -6 output, you should have a circle. So -1, 1, 2, 3, 4, 5, 6. See how my line basically jumps over that point and then keeps on going. This is called point discontinuity. Okay, and so now we're finished with this graph. That turned out to be a pretty easy graph. And let's try one more. Okay, this is number 16 from your homework. So first thing I'm going to do is look for factoring opportunities. There aren't any. So I'm going to jump right into seeing if I'm going to have any x-intercepts or zeros of the function. So I'm going to take the numerator, make it equal to 0, and solve it. So I should be crossing the x-axis at +3. Okay, now I'm going to look for vertical asymptotes, horizontal asymptotes, and I'll throw holes in there as well now that we understand more what those are all about. Since I couldn't cancel anything, I'm going to take whatever makes the denominator equal to 0 when plugged in for x. That would be when x is -1. So I'm going to have a vertical asymptote at x equals -1. Okay, now I'm going to check for horizontal asymptotes. Well, I have horizontal asymptotes when the numerator degree and the denominator degree are the same, and they're both 1. So remember that scenario that we talked about in class. It should be in your notes. Whenever the numerator and the denominators have the same degree, you're essentially going to make a line, and you're going to use the lead coefficients in a fraction. So that would be the line y equals 1 over 1, which is another way of just saying y equals 1. So I'm going to draw a horizontal line that is representing the equation y equals 1. Okay, so I'm still going to have a graph in basically two parts. The question becomes, will I have a part up here or down here? And then will I have a part up here or down here? Well, I think I've got that pretty much figured out, since I know that I've got this point, this x-intercept. Looks like this part is going to reside in this area down here. So let's go ahead and put all the pieces together, get a clearer picture of what this graph looks like by doing some inputs. All right, and so let me erase this so we can see this just a little bit better. So basically, you just want to know this vertical asymptote is the divider, and you're going to test numbers on either side. All right, so I usually just start just from the inside out, build out from this vertical asymptote. So my next available x number input is going to be -2. Okay, and if you need a calculator, that's great. Hopefully this is easy enough math to where we can just do this in our head. Let me erase these arrows so we don't get messed up. Okay, so if I add those two numbers in the numerator, -2 minus 3 is -5, and on the bottom I get -1. So that makes an output of +5, -2, +5. All right, and so let's just go ahead and do one more on that side so we can get a really good picture. We'll do input -3. So I'm just going to erase these. Input -3. I get -6 over -2, which makes +3. So input -3, output +3. And I'm pretty comfortable with what this is going to do. I'm going to be approaching this vertical asymptote, going up forever, and then I'm going to be approaching this horizontal asymptote in that way, going through those 2 points that we just came up with. All right, so we got one piece of the puzzle, and now let's start plugging in on the right side of my vertical asymptote, and we'll start with 0. All right, so let's see if we input 0 for both of the x's. That should be pretty easy. That's just going to make those x's drop out, and I'm left with -3 over 1, which of course is -3. So here's 0, -3. Okay, and I already have this point here. So I'm going to go ahead and do another input in between. Maybe just go with 1. If we input 1, we get 1 minus 3, which is -2, over 1 plus 1, which is +2. So -2 over 2 is -1. All right, and that's pretty good. I know that I'm going to be coming this way to -infinity. I'll just keep getting closer to that vertical asymptote, and going to +infinity along the y-axis, I'll just keep approaching that horizontal asymptote. And that's it. That is the graph of number 16. So you've seen a little bit of everything with these 3 problems: vertical asymptotes, holes, horizontal asymptote like you just saw in this problem. And so I hope these 3 problems plus the other one that's already done on a separate video, a total of 4 of the 10 problems that you had on the assignment have been done for you. But again, make sure when you're finished with this assignment that you understand this process. And if you have any questions, please let me know.